Welcome to part 4 in a series of videos on the drying of fruits and vegetables. In this presentation, we will examine factors influencing drying. My name is Don Mercer, and I am with the Department of Food Science at the Ontario Agricultural College, University of Guelph. We will begin with several acknowledgements and then have a brief introduction. We'll look at product attributes that influence drying and follow this up with the dryer attributes that influence drying. And we'll examine the effects of drying on the product and look at case hardening as a special consideration. Then we will close with some summary comments. I would like to thank Mr. Andrew Goodwin, Associate Industrial Development Expert with the Agribusiness Development Branch of the United Nations Industrial Development Organization, for his considerable efforts in coordinating this project. I would also like to thank those who are assisting in the presentation of this material to various local groups. Their contributions to our training activities are greatly appreciated. An important part of food drying is understanding how various factors influence the finished product. In this presentation, we will look at a number of the factors that you may encounter as you dry fruits and vegetables. We'll begin with basic shapes. We need to think of drying of materials in terms of characteristic shapes and dimensions. There are 3 basic shapes that are generally considered for drying purposes. They are flat slabs or plates, which I've represented here with this flat piece of wood, spheres as represented by these small balls, and cylinders as represented by this piece of wooden dowel. However, we should be able to relate these to actual food products. A flat slab can be shown as being a piece of mango. Spheres can be represented by berries such as these cranberries in the top right-hand corner of the slide. And finally, we can represent a cylinder with a carrot. Each shape behaves differently. In the case of flat slabs or plates, water travels from the middle of the slice to the surface where it is evaporated. Moisture loss is from the top and bottom surfaces, and the edges are not significant in the overall scheme of things. In the case of spheres, we have moisture traveling from the center of the sphere to the outside surface, where it is then evaporated. So moisture loss is from the outer surface of the sphere, but berries may be a problem due to the waxy skin that many of them have. In the case of cylinders, we have moisture traveling from the center of the cylinder to the outside surface, where it is evaporated. Moisture loss is from the side surfaces, and the ends may not be significant. So overall, the flat slabs or plates are generally the favored format. The manner in which a food material is prepared can determine how it behaves during drying, and I would like to use the example of carrots. Here we have some flat slabs or plates. Moisture is lost from the top and the bottom surfaces, and as was the case in the diagram in the previous slide, the edges are not really significant in the overall scheme of things. In this case, we have carrots cut into chunks, and they tend to behave more like spheres because the thickness of the chunk and the diameter are so similar that what we have is moisture being lost from the ends and even the side surfaces, so the sides tend to be significant. In the case of cylinders, we can simply cut a length of carrot and use that to represent the cylinder. Moisture loss is from the side surfaces, and the ends may not be significant. So once again, flat slabs or plates are the generally favored format. Continuing with the thickness and configuration effects, let's take a look at hot yellow peppers being dried at 50 degrees Celsius with an air velocity of 0.5 meters per second. What we are going to do is look at the effects of how we configure the pepper in the dryer. Here we have whole peppers, and as you can see from the photograph, they tend to have a waxy surface which reduces the rate at which moisture is lost when they are placed in a dryer. However, if we cut the peppers in half lengthwise and remove the seeds, we see a tremendous difference in the rate at which moisture is lost. Then we can quarter the peppers lengthwise, and once again we see a corresponding increase in the rate at which moisture is lost, and they will dry in a shorter period of time. Finally, we're going to cut the peppers into eighths lengthwise, and here you can see the green line has the fastest rate of drying of all of the others. So overall then, the amount of exposed surface area and the edges have a major effect. Some materials may have a waxy skin or peel, as in the case of many berries, as I have already mentioned. Here we have a plate of cranberries. The function of a berry is to provide moisture and nutrients for the seeds which it contains. Therefore, the berry will try to hold moisture in and not allow it to be lost. As a result, it is extremely difficult to remove moisture from whole berries. You need to be aware of the surface characteristics of materials like berries for drying. Here we see some cranberries in a dryer. Measures may need to be taken to address the potential problems that you could encounter. On this graph, we show the rate of moisture loss for whole cranberries and halved cranberries. So looking at the whole cranberry curve at the top, you can see that the rate at which moisture is being lost is very slow. Please don't worry about the vertical axis, which shows the dry basis moisture. This is an indication of the amount of water that is contained per gram of solids in the berries. But the important thing to recognize here is the downward trend and the rate of that trend. So once again, the slope of this curve is very shallow, and it will actually take about 7 days to dry these whole cranberries down to the desired final moisture content of about 10%. And of course, the berries tend to deteriorate after a prolonged period of time at 50 degrees Celsius in the dryer, so this is totally an unacceptable way of removing moisture. Now, by simply cutting the berries in half or rupturing their skin, we can improve the drying properties noticeably. And we have the example here of cutting the cranberries in half. Once again, you can see that we have a steeper slope on the graph, and we actually end up with a drying period that takes about 20 hours. Similar materials can have different moisture contents, which will affect how long it takes them to dry. Tomatoes with 93% moisture should dry faster than those with 95% moisture, simply due to the amount of water that is present. Product composition and structure is also something that has an influence on drying. You might want to consider the structure of a yam and compare it to that of an apple. The yam is rather dense or solid, while the apple is quite open and porous, and these differences have a pronounced effect on the rate of drying. There may also be structural and compositional differences between varieties of the same material, so let's consider some apple varieties. And here we have 3 apple varieties which are very common in Canada. On the left, we have a Royal Gala apple, in the middle we have a Granny Smith, and on the right we have a Macintosh, or Mac as it is often called. Each one of these apples has a different texture, and they will dry differently, and it will give you a different final product texture. We can also have seasonal variations. They can occur from year to year. So if you were to compare the drying of a product last year with a similar product this year, you may notice a difference, and this can be attributed to such things as differences in the growing season, which impact upon the structure of the product. We can also have variations through the growing season. If you take a product from the early harvest and compare it to a similar product taken at mid-harvest, their drying properties can be different. And the same thing happens when you compare early harvest or mid-harvest material with that taken late in the growing season. In addition to individual factors and attributes, there can be interactions between and among various factors. An example of this is surface area and thickness. Since moisture is lost from the surface, we want to have as much surface area available for drying as possible. Because moisture must travel or diffuse from the center of the material to the surface, we should try and minimize this distance as well, and this is actually the thickness of the material. Using thin slices reduces the thickness, of course, and it also increases what we refer to as the surface area to volume ratio, which is a good thing. In this diagram, there is lots of surface area per volume of this material. The more surface area available for a given volume of material, the faster the drying will be. And that's why we tend to cut carrots into thin slices. But please note, you need to use a reasonable thickness for handling and for the final dried product. For this reason, we tend to use a thickness of about 0.5 centimeters or 5 millimeters. A little thicker may be acceptable. There may be other factors not covered here. However, sufficient information has been presented to show just how important the attributes of the materials are in drying them. Now that we have examined the features of the material that influence drying, we should look at how the actual dryer can influence the drying process. Here is a graph that shows the results of drying mango slices in 3 different types of dryers. In the first case, we have dried the mangoes in an open-air dryer, and this is accomplished by placing the mangoes on a wire mesh that allows the air to blow across them. The sun will provide the heat in this operation, and that drying curve is shown by the shorter dashes of the 3 in the graph. In the second case, we'll consider solar drying that was done in a homemade dryer that I have here in our backyard. And what you see is that this dryer will remove moisture somewhat faster than the open-air dryer, and the curve for the solar dryer is shown by the longer dashes. Finally, we have a forced air dryer that was used in our research lab, and that's shown in the photograph. Here, the air was blown across the material at a constant rate and a controlled temperature, and this gave the fastest rate of drying and actually gave us more control over drying than the other 2 methods. So essentially we have open air drying not being quite as good as solar drying, and solar drying not being quite as good as forced air drying. But the important thing to notice here is that the type of dryer has a great influence on the drying of the material, such as the sliced mangoes. The temperature of the air is also an important attribute, and that can be controlled in forced air dryers. So in this graph, we show the drying of mango slices that are 0.5 centimeters thick with an air velocity of 0.5 meters per second. And we can measure the air velocity with a device called an anemometer. So what we have here then is a set of curves, the first of which is at 21 degrees Celsius. This was room temperature in the lab the day that these runs were done. And you can see that moisture is removed simply by passing air at 21 degrees Celsius over the surface of the mango slices. However, it's a rather slow process. and even after 16 hours, we are still having a drop in moisture, and this is not really the way we want to dry things. I should also mention that the vertical axis is a measure of something that we call the moisture ratio, and this is a technique that allows us to compare the results of numerous runs and get an idea of how they are relative one to the other. So now that we've done the run at 21 degrees Celsius, we can see what happens when we increase the temperature to 44 degrees Celsius, and there is a noticeable difference in the rate of drying. You can see how the moisture content decreases much more rapidly at 44 degrees Celsius than it did at 21 degrees Celsius. The next curve is colored red because that's the temperature which I tend to use in most of the drying runs in the laboratory dryer. And as you can see here, it has a faster drying rate than the 44 degrees Celsius temperature, but not nearly as much of a difference as there was in going from 21 degrees Celsius to 44 degrees Celsius. And finally, we have the curve for drying the mango slices at 60 degrees Celsius, and it is the steepest of them all, indicating that the mangoes dry faster at 60 degrees Celsius than they do at lower temperatures. However, do not be tempted to increase the air temperature beyond the range of 50 to 55 degrees Celsius. If you go much beyond 55 degrees Celsius, you are at risk of doing thermal damage to the product. Using temperatures beyond 55 degrees Celsius can result in changes in the properties of the material being dried. We will examine several of these problems later in the presentation. So please exercise caution and do not be tempted to go to elevated temperatures that are in the area of 60 degrees Celsius and beyond. Please try to confine your drying efforts to 50 to 55 degrees Celsius. We should also consider the velocity of the air. Here we have several curves for mango slices that are being dried at 50 degrees Celsius, and the thickness of the slice is 0.5 centimeters. The first thing that we'll look at is the effect of having an air velocity of 0.2 meters per second, and that's illustrated by the red curve. You can then compare this to the effect of increasing the air velocity to 0.5 meters per second while keeping the temperature constant, as well as using the same thickness of mango slices. From this graph, you can see that air velocity has a pronounced effect on the rate at which moisture is being removed from the mango slices. The rate of drying is noticeably faster with an air velocity of 0.5 meters per second than it was at 0.2 meters per second air velocity. 0.75 meters per second and 1.0 meters per second were tested and gave only small drying rate increases beyond that of the 0.5 meter per second air velocity. So after these tests were done, all of the drying tests in the lab were done using an air velocity of 0.5 meters per second. So why is air velocity a factor? To answer the question, why is air velocity a factor, we need to look at what is happening at the surface of the material. Remember, drying takes place from the surface. So let's represent this diagrammatically. Here we have a slice of material with a pool of moisture on the saturated surface, and that is the location from which the moisture is going to be removed, and that's where all the action is. In addition to the pool of moisture, there can also be a stagnant or non-moving layer of air that clings to the surface of the material. So here we have that slice of material with the pool of moisture on its saturated surface. Now what we're looking at is a layer of air that clings to the surface, and we call this a stagnant boundary layer. This stagnant boundary layer of air will become saturated with water vapor, and it will just sit there if there is no air movement to sweep it away. The result is that there will be little or no drying that can occur. If there is enough air movement, the stagnant boundary layer will be swept away by fresh, warm, incoming air that has a very low moisture content. So once again, we'll show the slice of material with the pool of moisture on the saturated surface. We'll bring heated air across this surface at a velocity that is sufficient to sweep away the stagnant boundary layer, and so what you see is that the stagnant boundary layer of air clinging to the surface has now been replaced by fresh incoming air, which can now evaporate moisture from the surface. The fresh incoming air now has the ability to pick up moisture from the surface by evaporation, and we'll indicate that by these two arrows that go upward and downward from the surface that show the fresh incoming air evaporating moisture from the surfaces. Failure to have a high enough air velocity can reduce the efficiency of a dryer. This is often the case in solar drying applications. We also have to consider the direction of airflow. Airflow across the surfaces of the material is preferred to upward or downward airflow, and we've already discussed that in the video presentation for part 2. So we have heated air moving across the surface of the slice of material, and uniformity and efficiency are enhanced versus the upward or downward airflow directions. We also need to mention the relative humidity of the air. Relative humidity is defined as the amount of moisture present in the air versus the amount of water the air can possibly hold when it is saturated with moisture at that temperature. It is expressed as a percentage. So if we have a relative humidity of 45%, this means that the air at that temperature is currently holding 45% of the moisture content that it could possibly hold when it becomes fully saturated with water vapor at that temperature. Relative humidity of the incoming air is generally not a problem if the air is heated to about 55 degrees Celsius. This is because warming the air increases its ability to hold moisture. Raising the temperature to about 55 degrees Celsius gives the air the ability to pick up a considerable amount of water in the dryer. Retention time in a dryer may be a rather obvious point, but let's mention it anyways. The longer the material is left in the dryer, the more moisture it will lose. So what we see here is that more moisture will be lost by a material after 8 hours in a dryer than if the material was in there for only 6 hours. Now let's look at some of the effects of drying on the product. Ideally, drying should have absolutely no negative effects on the product whatsoever. If the product is to be consumed in its dried state, there are certain product standards and expectations that must be met. If water is to be added back into the product, then the rehydrated or reconstituted product must meet the original product quality and performance attributes as closely as possible. Here we have some slices of dried tomato, and we're going to expose them to boiling water to rehydrate them, and the slices of dried tomato will then take up moisture, and here we see what they look like after they have been rehydrated. Dried tomatoes do not tend to rehydrate to their original water content. However, they do pick up enough water to make them suitable for use in cooking of stews and things of this nature. Drying presents the opportunity for a host of negative factors to be introduced into a food product. These may include such things as nutritional degradation. Many vitamins are unstable and they are highly susceptible to heat damage. So I want to show this using a very simple diagram. Here what we're going to do is plot vitamin functionality versus temperature. And there aren't going to be any numbers on this graph because what we're trying to show is a trend rather than actual observations. So if we look at how vitamins respond to a change in temperature, we can see a possible downward trend in their functionality as the temperature increases. Therefore, we need to keep the temperature within recommended limits. Loss of structural integrity can also be a problem. Stresses in drying may cause cells or the structure of a material to collapse inward during drying. Some products may shrink during drying, which is quite normal. However, the product should not shrink so much that it becomes too dense to take up water if we want to rehydrate it. There can be reductions in functionality. Functionality is really a measure or an indication of how a material performs under certain conditions. So for example, let's consider the changes in function due to heating, such as in the case of starch gelatinization. These changes impact how the material behaves when it is used. Naturally occurring starches in materials like Irish potatoes and cassava are ungelatinized until they are heated. If you dry an uncooked starchy material above 60 degrees Celsius, the starch will gelatinize or tend to go rubbery. Here we see some cornstarch powder that was dried under proper conditions that were less than 60 degrees Celsius. So if you wanted to use the dried starch to thicken liquids such as gravies or sauces, it would not work if the starch was already gelatinized. You need to take the ungelatinized starch and place it into the liquid, heat it, and then the starch will gelatinize while it is in the liquid, and that will cause a thickening of the sauce or the gravy. If the starch is already gelatinized, it doesn't function nearly as well. Color and flavor changes can also be pronounced. They are often due to toasting or browning reactions. And here I've taken a slice of white bread and toasted it to give you an idea of color changes. Some of the flavor and color changes may be desired, while other ones may not be desired. It all depends on the end use of the product. And of course, there will be textural changes that may also occur. Leaching of soluble constituents is a rather subtle effect and may be a bit difficult to visualize. Nevertheless, we should not ignore it. Basically, what we have here is water drawing soluble nutrients to the surface of the material as it travels or diffuses from the interior during drying. And these soluble nutrients are naturally present within the material itself. The nutrients are left behind when the water evaporates from the surface. These soluble nutrients on the surface can then be lost if the dried material is placed in water to cook or rehydrate. So let's show this diagrammatically. We will begin with a particle shown by this circle. Moisture moves to the outer surface from the interior, and as it does, soluble components will move with this water. The water will then evaporate from the surface. So looking over here on the right-hand side of the slide, we see that the material may shrink while drying, and we have the evaporation of moisture from its surface as shown by these arrows. Compounds are left on the surface as indicated by this green layer. They will become powdery after the drying process, and these compounds can be washed off during cooking. Now we need to look at case hardening. This is a very serious problem and deserves individual attention. Don't let it happen to the materials that you are drying. You need to use a great deal of caution to prevent it. Here's how normal drying should take place. We begin with moisture inside a slice of material. That moisture then diffuses to the surface of the material, where the warm air blowing across the surface will take away the moisture that is leaving the slices through a process of evaporation, and then the moist air will leave the dryer. So that is a rather gentle process that will carry on without too many problems if you use a reasonable temperature. When we use extremely high temperatures, we can get excessive surface drying that will create a tough, impermeable outer shell that prevents or restricts moisture loss. Often the product feels dry, but it is only dry on the surface. Severe problems can occur after storage or packaging. So let's take a look at what happens now when we dry using excessively high temperatures. What we have here is very hot air moving across the surface. This will create a dry outer layer around the slice, which is indicated by the shading. Moisture will be trapped inside the slice of material, which tends to shrink during the drying. As a result, little or no moisture will leave the slice, and this very hot air moving across the surface will only remove small amounts of water as it leaves the dryer. After packaging or during storage, the moisture trapped inside the outer shell will have time to diffuse to the surface. It may collect in certain locations in sufficient amounts to promote mold growth in the package. Case hardening is easy to avoid if you keep the temperatures of the drying air in the range of 50 to 55 degrees Celsius. There are numerous examples of commercial and small-scale drying operations failing because the product was case hardened. The underlying cause can be attributed to the operator's failure to understand the basic principles of drying. And in one case we worked with, the problem was encountered because the operators were trying to dry the mango slices at 85 degrees Celsius, and as a result, they were case hardening them, and the material was spoiling when it was stored. Had they dried the material at a lower temperature, and again I always recommend 50 to 55 degrees Celsius, they would tend to have a higher quality product that would not experience the mold growth upon storage. So in summary, the mechanisms by which materials dry can be quite complicated when you go into the actual details. Basically, the thing to remember is that water removal during a drying process is something that depends on time, and it cannot be rushed. There are things that you can do to enhance the rate of drying to a certain degree. You can consider things like material thickness, air temperature, and air velocity. However, there is a limit to these, and ultimately, you must respect the fact that moisture takes time to diffuse to the surface of a material where it is evaporated. Many drying processes fail due to the simple fact that the operators become impatient and try to push things with a total disregard for the basic principles. Please don't be tempted to fall into the common trap of using excessively high temperatures. So do not use temperatures of 85 degrees Celsius when you're attempting to dry mango slices. In the end, it is your product quality and safety that will suffer. Failure to respect the basic principles of drying is a major problem in far too many drying operations. Thank you very much.